Thank you, everyone. Hello, my name is George Asimenos. I'm CTO of DNAnexus. And without further ado, I'd like to invite our panelists up here, Laura Veer, Sue-In Lee, and Jeffrey Reid. So this session is going to have a slightly different format than other panel discussions. Each of the participants will come up here to the podium and present to you the latest and greatest about the challenges in applying AI in biomedical contexts. And then we'll have a little Q&A session after each person so that you don't forget what they spoke to you about in succession. So expect to be able to ask questions after we are done with each talk, not at the very end, because this way it can be more in context. Hopefully that makes sense. So if we are all ready, then let's start right away with our first speaker. I will introduce her. Her name is Laura Veer. She is Director of Applied Genomics at the Helen Diller Family Comprehensive Cancer Center at UCSF, where she leads the breast cancer oncology program. Among other things, she's famous for inventing MammaPrint, a gene test for breast cancer, and she has since then co-founded Agendia. She's involved in the I-SPY2 clinical trial, as well as the Athena Breast Health Network cohort study. And today she'll talk to us about the challenges of applying machine learning in the context of regulated clinical trials. Really good. Thank you.
Thank you very much, and welcome everybody. I would like to take the opportunity today to actually talk about the I-SPY2 trial and give you some introduction about the challenges to implement actually artificial intelligence into really understand what patients should be treated with what drug. So the title of my talk is I-SPY2, Getting the Right Drug to the Right Patient at the Right Time. So the I-SPY sorry, a little small here on the screen. So I-SPY uses biology and artificial intelligence, thank you, to adaptively guide treatment for breast cancer. And besides that, I work at UCSF. As said, my disclosure is that I'm also a co-founder of Agendia. So I-SPY2 is a platform clinical trial, and the basic principles is to test new drugs where they matter most. Actually, early stage, when patients are newly diagnosed, rather than metastatic disease, and change the order of therapy, learn about response early in the course of care, and evaluate at time of surgery if a drug has worked, and also use imaging. So we have built an efficient engine to evaluate drugs, accelerate knowledge turns by having one master protocol and an adaptive design across by now 15 different drugs. We're using imaging and biomarker guidance to actually get the specific drugs to the patients who actually respond. And we specifically focus on patients who have a high risk for early recurrence because they're most in need of getting better treatments today. We're using artificial intelligence to get insights who responds to what drugs. And the graduation is that the probability of success for a subsequent phase 3 trial is over 85%. It's a large collaboration. I'll show you my acknowledgement slide at the end, with the FDA, IRBs, pharma, biotech, academics, community cancer centers, as well as patient advocates. So the I-SPY participating sites are 19 across the United States. They are open and enrolling since 2010. We started slowly, but by now 2,500 patients have been screened to become part of the I-SPY2 trial, and over 1,500 randomized to actually evaluate these phase 2 targeted drugs. The I-SPY2 investigational drugs are given in addition to standard chemotherapy at the moment, and these drugs have all been developed targeting hallmarks of cancer. So many of you are familiar with this diagram where all of the different biological processes that can derail to make a normal cell a cancer cell can happen, and these drugs are targeting either one or two of these biologies, and we're using them as single agents or sometimes in combination. The I-SPY2 framework is that at diagnosis, there is an MRI to assess tumor volume and a biopsy to assess the biological subtype. Then when patients are eligible and they get randomized to a certain arm, the drug treatment Then serial MRI is used to verify volume change, and that, as well as the pathological response at surgery, are used to inform which predefined subtypes actually respond to a certain drug in the arm. As you can see here, we have multiple arms. There's one standard treatment, and there are up to 5 targeted treatments in parallel. So at diagnosis, biomarkers used are imaging, pathology, and the molecular biology so far has been to do the adaptive randomization on 8 subtypes defined by hormone receptor, HER2 status, and malprint high or very high. The adaptive randomization monitors the response, and at the time of surgery, the efficacy is determined based on pathological complete response. So how this works is that every new patient comes in the trial and is randomized. Her response is being noted, and also the early volume change is used in the adaptive randomization. And to long story short, for every patient that comes into the trial, if a particular subtype is starting to show more benefit from a certain treatment, then the next patient with that predefined subtype actually has a higher chance to be randomized into that arm. So we are enriching the arm for the patient who respond, and that's also beneficial for the patient because she has a higher chance to end up in an arm where actually her biological type of tumor will show a response. We've set a threshold where we can predict that, as said, in a phase 3 trial, there will be over 85% success in the next trial. So I'll show you some of how the mechanics, how this works, before I go into the artificial intelligence. So the biomarkers that we're using, for instance, are just standard triple negative or hormone receptor response. So here is a PARP inhibitor as combined with a carboplatin, one of the earlier drugs in the trial. And you can see on the left that control treatment as compared to this veliparib carbo combination actually doubled the response rate from 26 to 51%. Whereas in the hormone receptor positive patients, there was no added benefit of adding these targeted drugs in combination with standard chemotherapy. So during the trial, this arm was enriched for triple-negative breast cancer patients. And this is an example. If you look at the MRI of 2 breasts, where in the left breast in front of you, you can see the tumor, you can actually see that after 3 cycles, 3 weeks in this particular patient, the tumor is almost completely gone. And we see that for rapid responders actually more often, that in 3 to 6 cycles, the tumor is gone, yet patients are being treated for completion, which is 6 months, and I'll come back to that point later. But we're using this early response in the adaptive randomization, so very powerful drugs actually have a lot of information from this early MRI change. So over time, started in 2010, we have tested 15 different drugs, 10 completed evaluations, a few more are about to be completed, 7 graduated, 2 dropped for no increase of efficacy, and 1 was stopped for toxicity. 5 arms are ongoing. In these very small black and white boxes, the graduating subtypes are indicated for each agent, and I'll come to that later and show you another example on veliparib carbo. Most importantly, that for these women that have a high risk for recurrence, which normally means like a 60-70% risk of recurrence in the first 5 years, what we have shown that over 741 patients who had a median follow-up of almost 3 years, that those women, regardless of treatment, who achieved a pathological complete response, their 3-year survival is 95%. So if we continue to see that, we actually delayed or maybe even fully got the cancer out of these women by this early effective treatment. So this is a very important intermediate endpoint, pathological complete remission, and we hope to show continuously that it actually predicts longer time outcome. So now actually we've been working on these biomarkers, level 1 as I call them, the standard biomarkers, but we can actually do much better with response biomarkers to improve the response prediction. Because it's important to get everybody to a PCR because that's an increased probability of survival. And we want to use qualifying biomarkers, which is our level 2, to actually see if we can further increase the prediction of response. And those qualifying biomarkers go to a rigid system. We published that 2 years ago of being entered into the trial. If there's previous knowledge, they actually will predict response to a certain targeted drugs. So here are again these drugs that we've been testing, and for each of these you can see their targeted specific biology, and for most of them qualifying biomarkers exist, and we've tested their response predictors in how they predict response. So as one example, for instance, here's a list for the PARP inhibitor carboplatin treatment, where one knows DNA repair deficiency is indicative of response. And this is the list of biomarkers that we tested to see if we can increase probability of response. So based on the level 1 triple negative biomarker, this is what I just showed you, there is a duplication of response if you take triple negative patients. However, if we take a combination of these qualifying biomarkers, as shown here on the right, so they have a PARP inhibitor sensitivity signature and they are mammaprint very high risk, almost all responses in that group. The remainder of over half of the patients actually has no additional benefit. So it can be actually much better. And for these 58%, one actually would probably rather propose a different drug than having them treated for 6 months, something that won't work. So we went through all of these first 10 different arms, and here's just a snapshot of these qualifying biomarkers, which we could show you all individually, but I'd like to show you actually the next step we took. We're actually evaluating to a next phase in the trial, where we really want to maximize the pathological complete response, make use of this MRI volume early, and integrate all of these qualifying biomarker into one combined response signature set. So here is, for those who are working on data, if you take the first 1,000 patients in I-SPY across from top to bottom, 24 qualifying biomarker sets, you can see there are clusters of response. And actually these clusters of activity associate with certain drug responses, and they are pathways that are known for proliferation, DNA repair, immune signatures. There are also immune drugs in I-SPY, as well as HER2 signaling. So we actually went ahead and started to see if we can, besides those 24, if we can reduce the dimensionality to actually make this in a workable hypothesis that we can test in the next trial. So we want to find a minimal set that accurately predicts which patient will respond to what treatment. And there's a whole series of steps in this analytical part, as done by Christina Yao and Denise Wolf. And we actually ended up with 5 subtypes that are actually associated with response. I won't give you all the details yet, we've yet to publish this, but if you look here, from breast cancer receptor subtypes, the level 1 biomarkers, as I call them, to the drug response subtypes, which are 5, as I've shown you here. If you take the 1,000 patients of I-SPY 2 treated so far with known response rate, then on the left side you can see the different colors, yellow, blue, green, orange, what is the proportion of those signatures. And on the right you can see how we reorganize these patients into 5 different response signatures, where HER2 signaling, DNA repair, immune activity actually is determining in which group they end up. So what does this predict is that we know that the standard chemotherapy with no subtype selection, 20 to 25% of these high-risk patients will have a response. In I-SPY 2, by adding the targeted agents to the different arms, we have seen that increased the response to 40%. When this predicted response on the response subtypes actually predicts we can get this to a 70% response rate. So we're going to test that in our next iteration of I-SPY 2. So here's just a little bit of a snapshot what we're going to do. We will have one of the adaptive randomization steps that will be based on these 5 response signatures. We're working with the FDA at the moment and pharma companies to actually put this into a regulatory framework. So we're going to move away from these standard level 1 molecular subtypes and use this actually much more natural response biomarkers. So this platform trial, which we can go on and on adding new drugs, actually is patient-centers the best agent for their subtypes. What we'll implement is a second shot drug for PCR if needed, maximize the chance of PCR because that actually may determine the cure for this patient, and it increases of PCR for this high-risk population. Patients like this, investigators like it, industry like it, and we're also moving forward in advancing regulatory science. So of course, as already told you, this is a platform trial. There is a large group of people that work on all of the different aspects of the organization as shown here. And in my last slide, I like to highlight all of the participating organizations, 10 pharma companies so far, 6 biotech companies and academic groups, and sponsor of the trial is Quantum Leap Health Collaborative. Thank you very much.
How do you mitigate the challenge of doing all of that in a regulated context? The FDA is a collaborator of DNAnexus. I know they've started to think about how they're going to regulate the application of AI, especially in this really fascinating context of an adaptive trial. So I'd love to hear some more. I saw a glimpse of it in the slide, so I'd love to hear more.
Actually, before we started, as I have experience with MammaPrint and getting something FDA approved, it sort of made me think, okay, I want to make sure that actually what we're doing in science has a very efficient path towards patients. And so the way how we've been doing that, qualifying biomarkers has a number of rigid qualifications. They need to be done in a clear laboratory. They need to have prior evidence that they respond to a certain treatment. And we're actually operating for a lot of our biomarker analyses on FDA IDE approved platforms.
Okay, we have time for 1 or 2 questions from the audience. And I know there's someone with a microphone, so if someone has a question, please raise your hand and then the microphone will come to you.
You have a camera, but not a microphone.
We need AI to spot who has a question in this audience, I think. But. Okay, well, unless someone else from the panel also has something to ask, then we can go on to the next. Well, thank you so much, Laura.
Thank you.
Great. Next up, we have Jeff Reid, who is the head of Genome Informatics at the Regeneron Genetics Center and an avid DNAnexus collaborator. He's originally a physicist who now works in genomics. His team has sequenced more exomes than you have, and he analyzes those in combination with phenotypic data to make precision medicine a reality. He lives in Stamford, Connecticut with his husband, Jim, and 3 feline children, Sabrina, Lyndon, and Emil. Today, he'll talk to us about the challenges of applying machine learning in deciphering genomic variation.
Thank you, George. You all for coming, and let me dive right in. So the thing that I want to talk about today, there's a lot of things that people are doing. There's a lot of excitement in AI and the things that we can do with machine learning in large-scale sequencing in particular. But I want to talk about variant calling, which is a little bit weird because I personally consider variant calling to be kind of a mostly solved problem. But I'm going to explain to you maybe why it's worth kind of revisiting and kind of resolving this mostly solved problem. So let me first kind of just remind people about the Regeneron Genetics Center. As George said, we sequence an enormous number of exomes, and this is done from the perch of a large-scale sequencing facility that's embedded, entirely stitched into the lifeblood of a pharma company, that is Regeneron Pharmaceuticals. But the way this works for us, the way we do this is we do this in partnership with external partners. So we're really working with external people like the UK Biobank Group, the Geisinger Health System, collaborators in places like Columbia University Medical Center, so that we can get access to the most interesting data sets. The data sets like UK Biobank that have 500,000 people who are doing exome sequencing on all of them, where we can pair it with phenotype data. Or the Geisinger Health System where they're deploying actual genomic care into their healthcare system, and we work with them on getting the sequencing done and helping to understand how we can bring sequence data and phenotype data together. So this, all the things that we do are really in the context of these large collaborations, and that's going to be important in terms of how we can actually leverage these large-scale data sets to create a lot of labeled data that we can plausibly improve variant calling with. But I did want to mention sort of one more thing about the Regeneron Genetics Center and the technology side. We have a huge commitment to automation. And again, this is fundamentally important because the way we see automation is automation should infect everything that we do. So it is everything from the automated biobank that can hold 1.5 million samples. We have robots that do all of our sample prep. John Overton is here. He's maybe somewhere in the audience today. He and his team have done a phenomenal job of automating everything that happens in the lab so that we can sequence at the scale of 500,000 exomes a year. And then my team takes it, and collaborating with DNAnexus and working on AWS, we've been able to implement a lot of cloud analytics to really support that automation. But the place that we haven't really come into automation is building models to help interpret the data. And I say this very intentionally because I want to frame the way we're thinking about machine learning and AI as just, it's another step in the automation cascade. We've automated the lab, we've automated the deploying of analytical pipelines. Now we're going to think about ways of automating better the way that we can extract information from the data. So the way I like to think about the sort of traditional set of variant callers, the things that people use every day like Edico and Sention and GATK and WeCall, there's literally probably hundreds of them now, is really these are human-built model rule-based callers. This is where we identify the type of variation we're trying to find. So for example, we might be looking at germline variants in exomes as we do with short-read exome sequencing data. So then we have to think about how the variation is represented in the data. So with randomly placed shotgun reads, little short reads placed all over the genome, we can have a reference homozygous state where we see all the evidence agrees with the reference, or variant homozygous where it all agrees with the variant, or a heterozygous, right? This kind of like coin flip thing. But then we also have to think about what are the error modes. So sequencing errors, sequencing technologies aren't perfect, so there's a sort of a low level of an error rate. Well, that changes a random base here and there, and coverage in high GC regions is depleted because of chemistry reasons, and genomic variability makes it difficult to kind of place reads. So people have, very smart people, with tools that are, by the way, very successful. Remember, this is a mostly solved problem. These tools work extremely well after sitting around and thinking carefully about the rules and implementing a tool that can extract variation. But what's sort of the new way of doing it? How would we automate this rather than having people think carefully about the problem? Well, the deep variant tool is the thing that we're approaching, and Andrew Carroll is somewhere in the audience, hopefully. And we're working with him and the Google team in thinking about how we could bring in-house this idea of a computer-built model, a kind of a database caller, where instead of doing the work of thinking about how variants should look and then building a model to extract that, do the work to build a whole bunch of variant calls and label those as accurately as possible, and then come up with a curriculum that can train the model so that it can give you the answer to the questions that you're trying to ask, right? And you, of course, do this best practices iteration on the building of the model and have a held out training set, or a held out validation set, and right, to get to a model that is good enough that you can then do variant calling. So, come on. So how does this look? How does this work? So it's maybe sort of hard to see here, but this is an actual screenshot of IGV, which is a standard viewer that people use to visualize this data. The gray bars are the individual sequence reads that have been put back into the context of the reference. And wherever you see a thing that isn't gray, that's where there's an apparent difference between one of those reads and the reference. So the way a sort of traditional caller would work is it would go site by site in this, and it would look for something like that thing in the middle where the black arrow is, this line where kind of like half of the reads have a little green dot and half of the reads have a gray dot. And if that meets the requirements of the rule-based caller, that gets called a variant. Very different with the kind of like machine learning based model, because what you do is you basically just have identified candidate sites. You would go across here and you'd say, well, there's enough variation at that site that I think it might be a variant. And then you would take that and you would show then this image, or a representation essentially of this image and some of the other data that is contained sort of behind it. And then it would make a judgment. It would make a classification about whether this is a reference homozygous call, a variant homozygous call, or a heterozygous call. But this is not always so easy. So I wanted to show an example. This is a region of the genome that's highly variable. Again, real data. Some of these variants may well be real. Some of them are probably sequencing artifacts. And so coming up with the good labeled candidates that are relevant to problems like this, not just the really easy variants, but the variants that appear in regions that are much more complicated, that's really what it's about, is how do we come up with those labels? So I think of this as kind of like a conservation of work. As an ex-physicist, I like conservation principles. So whenever somebody tells me, oh, I have this great method for solving everything and it's sort of like magically just does it, it's all easy, it's like, well, somebody had to put in some work somewhere. And the work that you put in here, as opposed to the human-based models, where the primary effort was kind of model definition and construction, and when the model is kind of wrongly defined, the results don't really solve the problem. So for example, germline variant models are not very good at capturing somatic variants, because somatic variants just don't match that kind of coin flip distribution of alleles that you would see, for example, in a heterozygous variant. But in computer models, computer-built models there's still work that people have to do, right? You have to understand the data and the errors well enough to make sure that you're getting accurately labeled data. And the primary effort then comes down to getting that labeled data and then building that curriculum. And the example I wanted to use here, as George pointed out, I have my feline children. I like to feature them in a talk in some way. And so I wanted to show an interesting example of a model that doesn't actually speak to the question that it's trying to answer, in part because it was given a curriculum that wasn't relevant to the question. So this is, and it's maybe difficult to see, this is from an AWS Deep Lens. So this is an AI-enabled camera. You can load kind of an out-of-the-box cat-dog classifier model. And the use case I have for this is I want to put this in my kitchen counter, and I want to be able to see when the cats jump up on the counter. I want to see that a cat is now in the image. So after a great evening, a fabulous dinner with George and Dick Daly from DNAnexus, he was able to source for me these great example objects. So we have this dog on the left, which you can see in the upper left is classified as a dog, and this cat on the right. These are little stuffed animals. There's a cat on the right. And then my cats very helpfully decided to come and help see if we could confuse the classifier. So Lyndon, when he sort of turned a little to the side, you see it classified it as a dog. And when Lyndon and Emil are together in the image, even though there's this stuffed dog there, it gets classified as a cat. So this is relatively successful as a cat-dog classifier. It can see the stuffed cat, call it a cat, see the stuffed dog, call it a stuffed dog. If it has confusing data, it doesn't always get it right, but it does okay. But here's where it's kind of irrelevant, right? Here's where I will need to not just take the out-of-the-box model. I will have to come up with a curriculum that's more relevant to my use case, because this model actually defaults to cat. So as a cat detector, it is completely useless. The idea of setting it on my kitchen counter and letting it just sit there and watch and see when a cat jumps up on the counter, you can see when the cat's in the image, it's a cat. When the stuffed cat's in the image, it's a cat. When there's nothing in the image, it's a cat. When I block the camera, it's a cat. It is not useful. And it's not that it's not useful because the model is wrong. It's not useful because the model was not trained to the use case that I needed. So it's really both about having the labeled data. I have a lot of cat pictures, as you might imagine, so I have a pretty good database of labeled data. But it's really then thinking about what the curriculum would be for the classifier so that it could do this. So that's a little bit of a fun example. Now I want to try to convince you that we actually have one of the largest sets of labeled data with which we could use to train a model. So just taking our data by the numbers, we've sequenced over 500,000 samples now at the RGC. For each exome, we get about 75,000 what I like to call Goldilocks quality variants within the target plus buffer region in the exome. We also do genotypes on every sample, and this is fundamentally important because The overlap between the genotypes and the exomes is about 75,000 bases, and going into the data, we have around 5,000 non-reference calls per sample in that overlap. So for every single sample, we have 5,000 non-reference sites where we have concordant calls between both the exome and the genotype. And I would argue that each one of those is a correctly labeled, validated call. So that gives us 2.5 billion labeled, validated calls, just from the overlap between our exomes and genotypes, thinking from the perspective of what would be candidate call sites for deep variant. So now I'm not going to show and go into this slide other than to say we also have a lot of relationships in our data. So this is showing the fraction of sharing between individuals. Most studies, everybody's in the lower right. They are third degree or more distant relatives because people like to have genetic studies where they can trust independent sampling, where people aren't related to each other. When you work in a healthcare system, mom and dad see the same doctor as their kid. And so you end up with a lot of families. And what that gives us is 2,600 trios. And well, why are trios important? Because trios, again, allow us to produce an increased set of labeled data. So we assume basic human Mendelian genetics is correct. So one allele from mom, one allele from dad, we're going to ignore de novos. And at the end of the day, because we have about 100,000 deep variant candidate calls from each exome, and we have about 10,000 trios, we can label every single one of those variants that are seen in the child as to be whether or not they are consistent with the calls that we see in mom and dad. And that gives us another billion trio labeled calls that we can use to train deep variant. So what we're in the process now of doing is then taking a third set, taking all of our data, something on the order of 10 billion calls, and using all of the high confidence kind of classic human-built callers that we can to create a gold standard truth set running different callers across the same exome data. This is now not validated by Mendelian genetics, it's not validated by orthogonal technology, but still it's on the order of tens of billions of calls. So even if we restrict it to only the highest quality calls, we have on the order of, sort of physicists talking here, on the order of about 10 billion calls that we can then use to define a new curriculum and retrain deep variant, which we think will be incredibly valuable on our data because our sequencing processes are so consistent that once we learn the error mode, the vagaries of the way that the capture affects GC content and the way the alignment impacts various regions of the genome, that we'll be able to do vast improvements on the existing models. So I just wanted to end on the idea of what, in doing this exercise of thinking about, well, we have this solved problem, but let's take it seriously in this new context. What are the things that I kind of learned about challenges in applying AI data on biomedical data? And there's kind of three things that I would say are take home. So one is scale. It's really, really hard to get incredibly large biomedical data sets because it's incredibly hard to gather a lot of accurate biomedical data. It's just a fact of life. The labels is the other thing. I think I may have convinced you, hopefully, that we have a really unique data set and we actually kind of out of the box have a lot of labelable data. So we actually have a very large scale labeled, accurately labeled data set for variant calls at least. But this actually gets much harder when you get out of the variant call space. When you start thinking about labeled data, whether it's images or whether it's phenotypes that have been extracted from electronic medical records, it's extremely difficult to get to billions and billions of data points that have labels. And then finally, the curriculum really matters. It's not just a matter of wanting to do machine learning or AI. I think there's a lot of impact that can be had, but it's thinking very carefully about how you're going to train it and for what purpose, because you don't want to end up with a cat classifier that doesn't ever actually see anything other than a cat. So I just want to acknowledge all the people who did it. I specifically want to acknowledge the AI models in case they're listening. I don't want to piss them off. And at the end, I just would like to say we're growing and we're hiring at the RGC. It's an incredibly exciting time to be in this field. So if you're interested, come talk to me or check out our career site. Thank you.
Thanks, Jeff. This was great as always. I did have a question to start it with. How much is this prone to the choice of reference genome? We know other things like the Asian Genome Project, and Korea has tried to also assemble another reference genome. Maybe the UK Biobank will want to do a British equivalent. What is your...
So my general feeling is as long as you pick a reference and you stick with that reference, it doesn't necessarily matter so much which reference you use. Now, I'm specifically talking now about small SNP and indel variants. If you want to talk about large haplotype variants or structural variants, then using maybe a more ancestrally relevant reference genome would be useful. But as long as kind of everybody's on the same page about what the reference genome is and you're looking at these small SNP and indel variants, I think the reference doesn't matter that much. But it has to be kind of consistent across projects.
And I know you touched on it, but I do want to ask you explicitly. A couple years back, we actually had a panel discussion at the DNAnexus user group meeting with folks from Deep Variant. And at the time, you made a comment from the audience that this is a solved problem and who would want to use it necessarily and whatnot. So what is this improvement or use case that you are trying to solve that is not necessarily a solved problem? And I'm saying also because we've been involved with the FDA that has run a ton of computational challenges and everybody is up in the 99.9% accuracy or
right. No. I mean, it's a very fair question because I say all the time, people who know me, I'm not in the business of solving problems I don't have. And so if variant calling is a solved problem, it's not a problem I have, so why am I doing it? There were sort of two things. One is I became convinced recently from some of the data that I had seen actually from Mark DePristo and some other people at Google that the costs were getting better. Like originally the sort of cost of running this kind of machine trained model, I wasn't convinced that it wouldn't kind of blow the budget. And then the other piece was both realizing that I had billions and billions and billions of kind of ready to go pre-labeled variants and the recognition that most of the variant kind of characterizations are happening only in these gold standard regions. I started to think, I actually don't know. I know that we've solved it mostly in the regions that we mostly look at, but I don't know if we've solved it yet in the regions that we rarely look at. And so while that's a much narrower space, there could be some really important variation there. And so I think we are missing something. And so that's why we kind of changed our minds a little bit about like, well, let's think about what we could do with this. Yeah.
And so as you train a really complex model, you throw all the information you have from every sample, from the variation for the mapped reads or even other information, and you generate a ton of features, and then this black box creates the perfect classifier. Do you care at all about the interpretability of these results, knowing what exactly from the input?
So the beauty of biology, and particularly the beauty of variant calling, is like there's an arbiter of facts, right? You can go to Sanger sequencing, like I can really validate some of these calls. So I'm less concerned for variant calling about unpacking the insight that got me to accurate variant calls, because it's sort of like a differential equation. Once you have the solution, you're done, right? For someone's health care, I think you will probably need to understand much better what is inside that model, because I can always reprocess a sample. You can't resave someone's life.
We have time for one question from the audience, if there is one. Over there.
This is Jason Chim from DNAnexus. I just want to question one thing about Devin Kohler this morning talking about SHAP. She talked about like collect all the meta informations, like the temperature, the batch, all the machines you run that. I mean, you have this really great unique data set. Do you think those extra metadata will help because this is very important?
Yeah, no, this is a very good point. So back when I was at Baylor, when we got our very first crack at PacBio data, our very early PacBio machine did not work because the humidity in the lab was too high. Apparently the standards for indoor humidity in Houston are different than California, go think, right? And so that stuff can be incredibly important. I would say that we know we don't capture all of that data in our LIMS and attach it as a fact to a sample, so we wouldn't have all that. That said, we have a very automated process that actually captures probably a lot more data into our LIMS about the sample prep and about the process of the sample through the lab and through the informatics than I would guess most labs. And so the place I would start is really with the easy things, the stuff that's contained in BAM files, but the next place to go would be to pull in all of the information information that's in our limbs about every single sample. And I think plausibly that could ferret out, actually this is getting a little ahead of myself, but that could ferret out not just improvements in variant calling, but it could also give us better information back to the lab when something goes wrong, or maybe when something doesn't go quite as right as it could, and they can maybe use that to improve their process.
All right, thank you so much, Jeff.
Thanks, everybody.
And our last speaker is Sue-In Lee. She's professor at the School of Computer Science and Engineering, University of Washington. She completed her PhD in 2009 at Stanford University with Daphne Koller when I was there as well. And it's no surprise that she has since received the NSF Career Awards and a whole lot of other accolades. Her research is at the intersection of computational biology and machine learning with an emphasis on interpretable machine learning. And she recently made it to the cover of Nature Biomedical Engineering for that. So I'm really, really excited to hear about the challenge of interpreting machine learning.
Thank you for, hello, can you hear me? Yeah, thank you for the introduction. Today I'm going to talk about some of the ongoing research efforts that's going on in my lab on developing machine learning techniques to improve the interpretability. So these days in medicine, we use machine learning in pretty much the same way. So for each patient, we use a set of features from this patient, from various sources of data. And then we fit that into some machine learning predictive model to produce some prediction of a clinical outcome. And then obtaining such a model is very easy these days. Even an elementary school student can download the machine learning software and then train on your training data such that you can get a good accuracy. Is that, then is my job done as an AI researcher? Certainly not. When you have a prediction result like this that is shown on the slide, a natural question is why? And then, even the machine learning researcher who built the system will say just AI magic, trust it. So the important missing piece here is the explanations. For instance, it doesn't tell you why the features selected by the machine learning model make sense, and then which features contributed to your prediction. And then these explanations can be very important because some of them can be really informative about how to come up with the appropriate clinical actions. So this led me to identify two really important problems we need to work on, we need to address to improve machine learning such that it can be actually useful in medicine. So first, learning interpretable feature representation. So we may be able to pre-select or learn interpretable features to begin with from the first place. So especially, this is incredibly important when you use molecular data, such as gene expression data or genetic data, and then you can perhaps your prior knowledge about the knowledge we already have on the susceptibility of the, how that gene's impact on the disease. And then it's mainly exemplified in our previous project on using gene expression data to choose anti-cancer drug out of over 100 anti-cancer drugs. It's published in Nature, it's distorted in some way, and then it's published in Nature Communications earlier last year. And then second, when we use a time series data, we need to somehow transform this time series data into a form a machine learning model can actually take as input. And then the question is how to transform these data in such a way that we extract important information. At the same time, we want it to be still interpretable. And then sometimes, we need to deal with a situation where not all features arrive at the same time. So let's say that there's a trauma patient. Some information will come from dispatcher's report. Some will be measured by paramedics or ER doctors in ambulances, and then emergency rooms. And then the question is there a way to use the features that already you have, and then can we use that knowledge to guide which other features should be measured in a way that you have accurate prediction and also fast prediction? So, and then second, we need to make interpretable predictions with some kind of explanations from this black box complex model, such as deep neural networks or ensemble models. And then to do that, we can estimate the importance of each feature on a particular prediction so that we can reveal individualized risk factors and their interactions. So next, in the next part of the talk, I'm going to talk about our recent project, one of them, which exemplifies how these explanations can be actually effective. It's about surgery and anesthesia. So surgery and anesthesia are an integral part of healthcare, but they pose a considerable risk of complications. And then in this project, we focus on an unwanted physiological condition called hypoxemia. It means low blood oxygen level that can cause a serious patient harms. And if hypoxemia can be predicted even 5 minutes before it occurs, then anesthesiologists can take some action to proactively prevent hypoxemia or mitigate patient harm. So for that, we developed a machine learning technique called prescience that can predict the near-term risk of hypoxemia during surgery. It's a real-time prediction, and it explains the factors that led to that risk. So how does it work? So prescience takes as input about 20 static features that include the surgical procedure, BMI of the patient, gender, age, and so on. And then about 45 dynamic features. This is time series data measured on a minute-by-minute basis, such as heart rate or blood pressure, blood oxygen level, and so on. And then it makes a real-time prediction in some form of a numeric representation of hypoxemia within the next 5 minutes. Okay? And then its a key feature is the ability to explain why a certain prediction was made. So in this example, it shows the risk is due to the patient's BMI, which, by the way, is not modifiable. I mean, it's only a couple of hours, and can you change the BMI of the patient? And or, slides are not progressing? Oh, sorry. Yeah, it was actually progressing. Oh my God, why is it blank? I see these slides here. Okay, all right, so this is the correct one, I think, right? Okay, so patient BMI or current tidal volume and then pulse rate. And then these explanations can be clinically important because they can inform the doctors what appropriate clinical actions can be taken. So how did we build this system? For any machine learning model, we first need to use the training data. And then we were working with incredibly supportive collaborators, Jerry and Bala. And then, because it's not synced actually. Yeah, okay, I will see that slide then, that part of the, okay, so, and then we obtained the AIMS data from 150,000 procedures performed at the UW Medical Center and then Harborview Medical Center. So then, so my PhD student, Scott, he played with various kinds of predictive models using this training data and then to measure its prediction accuracy, performance. And then it turned out that two best performing models are first, the linear model, that's simple model, interpretable model. The weights of the linear model will tell you which features are important. And then the actually best performing model is the gradient boosting model. It's a ensemble tree model. It represents a complex black box model. And then the performance difference is quite big actually. So, and then as a machine learning researcher, we are really familiar with this kind of a situation when you have a trade-off between accuracy and interpretability. So what does that mean? So with a modern, large data set, typically the complex models such as the neural nets or ensemble models perform better than linear model, but it's often considered as a black box, and even experts sometimes struggle to interpret it. So to address this challenge, we developed a machine learning method called SHaP that can focus on just one prediction, one patient, and then tell you the numeric score. It measures the importance of each feature for that patient, for that prediction. So in this slide, it's shown as the phi 1 through phi p, and then that can break this tension between accuracy and then interpretability. So in the end, we can then use this kind of a complex machine learning model that gives you high prediction rate in a way that it's actually interpretable. Okay, so how exactly can you then compute this feature importance, these phi values, and then we call them Shapley values. And the SHAP or SHAP values, this is from 1950s a game theory called the Shapley theory. So I'm gonna tell you what it is all about. So let me first, just to show how it works, let's consider a very simple, intuitive example. Let's say that there is a John. He's a typical bank customer, and then like other bank customers, when he applies for a loan, his information is sent through some predictive model, and then it will generate a prediction such as, what's the chance that John will have a repayment problem. Unfortunately, in this case, it's 55%, and then the bank declines his loan application. So here, the natural question is again, why? And then it's AI magic. It's all AI magic. So then, so how can we then, so what is the explanation for that? So let's say that the base rate of this having the chance that any customer will have a repayment problem is, what is it written? Because it's not, my slide I see is not synced with the slide shown. That's why I'm having a little difficulty right now. So it's 25%, and then John's risk is 55%. The question is, how did you get there? So let's say that then, let's consider each of the John's features. So it's like patients, BMI and age and sex and then many others. So in this example, you will be first age. Let's say that it adds the certain percentage to the feature, and that's, you can attribute that to the, the increase in risk. So that's the importance of that feature, age feature. Say that, what about John's occupation? So it's not, necessarily the most stable job these days. So that adds to the risk of having a repayment problem, and then open account, and then married. What does it mean? I don't know. Maybe like income is combined between spouse. So that reduced the risk, and then you arrived at 55%. So that's the explanation. So then but it's really important to understand that here the order matters. What does that mean? Let's say that, the occupation feature, the day trader, it may be particularly increase the risk more if you know that that is a young day trader. What that means is that, if you reverse the order between day trader and then age, it could be that the age is important, is more important than day trader factor shrinks. So depending on, in what order you introduce these features, the importance measure can be different. So then, so SHAP values, our method then, what it does is that it takes into account all possible ordering. So there are n factorial, if the number of features is n, then there are n factorial possible orderings, and then it's average of, average importance of all possible orderings. How can you compute that? Then you need to have some efficient way to compute these values. And then we showed that we actually theoretically proved that there is only one solution that satisfies the three very important properties that enable us to actually compare the importance of all these features. And then if you don't satisfy these three properties, you can't. So we show that our method is a theoretically proven optimal method. And then, again, the question is we need to develop specific, the machine learning algorithm that can actually compute efficiently. And then it's our current and then ongoing research. So let's turn to the prescience problem. So here is what we hope the anesthesiologist to see during the surgery. So it shows the hypoxemia risk. In this case, it's 2.4-fold risk, and some risk, it's not a lot of risk, and it also shows the factors that increase the risk, the purple colored, and then the green colored is the factors that decrease the risk. So, and then the plot at the bottom, it's equivalent to the importance of the feature you just see, and then turn that, rotate it by 90 degrees and stack them horizontally. Then you can see the trend of it. So in this particular example, actually hypoxemia happened in the next 5 minutes, and then the reason was that the tidal volume features, the patient tidal volume is amount of gas exhaled per breath, and then it actually, this patient showed a decrease in tidal volume, and that was the largest that contributed the most to the risk. And the tidal volume is, by the way, it's a ventilator setting because patients don't breathe by themselves when they are under anesthesia, so they are connected to the ventilator, and then you can adjust to that. So, okay, so now here is a really interesting part. So we then tested this prescience system by connecting to see whether physicians can actually perform better when they are assisted by this system. So we worked with 5 practicing anesthesiologists. These are all UW professors. They are very good people, not that like residents or fellows are bad, but they are just less experienced. But anyway, they are really good. They're very experienced people, and then we compared their prediction performance between when they are not assisted by prescience system. So they basically have the same input as the static feature and then the dynamic feature, the green colored box. And then when they are actually assisted by the system, when they show the whole part of the prediction results and then explanation. Here is the results. So they can, so in terms of the ROC curve, when anesthesiologists anticipate 15% of the event, they can, with the assistant, they can actually anticipate 30% of the hypoxemic event. So the next thing we tested was that what happens if we let the prescience predict the hypoxemia. So interestingly, when you just use that prescience system, you can predict a little better by when anesthesiologists are assisted by the system.
Yes.
I'm not going to add more comments to that on this result. So as a follow-up research, we are now developing machine learning methods that to efficiently compute the SHaP values for particular model types. And then we chose 3 ensembles. Why is that? Because it's extremely popular model, especially many of the Kaggle competition winners used XGBoost. Another UW professor, computer science professor, developed this package, and then it's a fast implementation of a gradient boosting model. And then here is a result of the Kaggle data survey done by a couple of data scientists, and then it shows that between linear model and then neural network, it's all 3 models. So we designed the 3 algorithms that reduce the exact computation of these SHaP values from exponential to polynomial time, and I will show you in the next slides that can enable actually exciting applications. So as a part of this 3 SHaP work, and we developed a rich visualization of the global importance of features across many patients, and we call it SHaP summary plot. So how does it work? So to explore this visualization, we used enhanced data from 100,000 individuals who were interviewed and then tested in the 1970s and followed up for 20 years. And then we extracted 14 common measures and the demographic data for Cox hazard model to predict mortality. How, what's the chance that the patient is going to die in the next 20 minutes? So for each individual, we can again compute the SHaP values. They will have different feature attributions, and then for each feature, and we can also see the distribution of these SHaP values. Here, the high value is colored in red, and then low value is colored in blue, and then you can see that for all the other features as well. So it's not surprisingly, age has the largest effect on the mortality, not surprisingly. Yes. So we see that some, and then overall, many features show some long tail reaching to the right, but not too much to the left. And then, for instance, the systolic blood pressure, it has a large impact only for a small portion of the individuals who show high blood pressure. What that means is that there are so many ways to die younger, but there are not many ways to be out of the range and then live longer. Said. So, and then another interesting visualization is the rich replacement alternative to partial dependence plot, and we termed SHaP dependence plot. So it shows you the SHaP values of the feature for each feature in the y-axis and the value of the feature in the x-axis. So by plotting these values for many individuals, so each dot is an individual, and then you can see the features attributed important, how it changes when the value varies. And then you can also see the interaction effect. The vertical dispersion actually means it's interacting effect. So if you focus on all the red colored dots and the blue colored dot, you can see that the systolic blood pressure is more important, more alarming factor for mortality for especially young people. So this is last slide. So SHaP method can also be used explaining model errors as well. So, and you know what happens when we deploy a machine learning system in practice? Like everything else, it breaks. So what's worse, when it breaks, it only gets less accurate, and you have no idea what was the problem. So take, for example, deploying a, it's happening again. So a trained to predict the duration of the surgeries. Duration prediction is really important for scheduling ORs. And then if you are a careful data scientist, you will monitor the average error. And then as the example shows, it just oscillates. It doesn't show you, obviously it increased or decreased. It increased a little bit, but what happened is that after 1 year of deployment, we switched to ORs, operating rooms. Not real operating rooms, on just the data. It would be a crime if I actually changed the operating room. So then if you see the SHAP values for these room labels, so you can see, right at the moment when we switch these OR rooms on the data, and you can see the drastic increase of the SHAP value. So you will know that you will now know 3 things which you didn't know about. First, the problem exists. Second, what was the problem? And then also how much that impact the accuracy of the model. So I want to thank my incredibly brilliant group of students in computer science and MD PhD students who were brave enough to choose computer science as a major, and then a group of collaborators from many departments in medicine. This is only one example where we showed that new machine learning method can open a new exciting way in treatment, and then a set of funding support. Thank you.
Thank you very much, Suyin. And thanks to the panel again for talking to us about the challenges of applying AI in biomedical context. And thank you for coping through the challenges of the AV.